welcome to the welcome last class. We have all that we have is no slides. We have just a few notebooks to go through, and so we're going to talk about clustering again a little bit, and then take a look at simple techniques for dimensionality reduction. I feel like this is a huge topic, also one that I don't have that much direct experience or research experience myself. So be kind. And let's see. So this K-means example to fill is the first things that we'll take a look at. And so we're still talking about the same algorithm, K-means, which was this simple idea of if you have a distribution of points in feature space, the idea is you select some initial guesses for the centroids of your clusters, and then we've seen that you can do it randomly, but it's probably not the best in terms of helping the algorithm find the optimal solution. And then you assign every point to the current closest centroid, and this gives you your first tentative cluster distribution. Then you calculate the geometric mean of the coordinates of the points assigned to each cluster to find the new centroid, and basically you repeat these two steps of assigning points, recalculating the centroids until you reach convergence. And of course, convergence in this case, as we have seen, doesn't mean you have found the optimal solution, or the global minimum of your optimization function, which is the sum of the square distances for every point in each cluster summed over all the clusters. But in general, it means that results are not changing anymore, and so there is no advantage in continuing to run the K-means algorithm. So let's take another look at this, and most of this example actually comes from this Python Data Science Handbook by Jake Vanderplas, which is a really great book. I think I had it in the class page, but if you guys want to look further, it's a really nice. You can buy the actual book for $28, but all the notebooks are online and free. So it's also a nice resource to have. Okay, so one of the nicest functions that we have, well, I'll do some imports here. And if you want, you can follow along. And we're saying make blobs. And this is a function that basically generates blobs of points. And in this case, we can say how many we want and how many centers. And so here, if you want to look at in this example, you have 4 blobs. And this cluster standard deviation, this is a parameter you can adjust to see how results change having points more clustered around or more spread out. So far I put it like this. And by the way, this also generates a true label. But because we are trying to implement an unsupervised algorithm, we're not going to use the true labels. And we're just going to see if the algorithm is able to pick these 4 distributions. Does it look like an easy problem or difficult problem? Easy-ish? Right. The only place where I can see a little bit of an issue is maybe here. Right? And this is a case in which I'm going to bet, or we could even check, that if you tell the algorithm I'm looking for 4 clusters, as long as your initial guesses for the centroid are well separated enough, I expect that you will be able to find them. But you can see that if we were to say, okay, I don't know how many clusters I have, guess it. I think that probably a solution with 3 clusters would be similarly good. And that's why, as I will try to show you a little bit later, I am a bit skeptical of using this type of unsupervised approaches completely unsupervised. And I think that the limitation of K-means, but actually a lot of these clustering algorithms that you have to tell in advance how many clusters you have is quite important. I think that even if there are methods to find the optimal number, I believe that in most science applications, they're not quite helpful. And so I think you always have to peek and see and adjust. Doesn't mean they're not useful, it's just I feel like it's not as unsupervised as it sounds. Anyway, with this one, and you can see that if I put 0.3, they become more separated. If I put a larger number, they become more spread out. So let's go with this one. And let's see, now we have to implement an algorithm, so there's not too much to fill. just because I can't remember much of the syntax of the various things, and so I just kept it to the basics. But I thought, okay, at least here we say from sklearn cluster import k-means, and then now we have our algorithm, and then let's give it a name like k-means. Ooh. K-means equal k-means, and then usually we have to give some parameters, and at the very minimum we want to say n clusters equal, in this case, what should I put? 4, right? Just because, like, okay, I have the luxury of being able to look at the distribution and guess how many clusters there are. Okay, I can do that. And then I guess, see, I already don't remember what the solution is, and I don't think I even have a cheat sheet for this one. So let's see. We can create from that a new vector that has basically the predictions of, like, the assignment of each point to a certain centroid, and I believe this is fit predict, and then my distribution of points, which was called x. And then once you fit the model, then the centroids will be available in, this should be, I think, lowercase. Let's see if I'm doing things right. And then centroid will have, there is a property cluster centers that will tell you, okay, where the guesses for the centroids are. So let's see if I wrote this right. I'm not super confident. Okay, something happened. So let's see. So what would be the possible y-means values? This vector of prediction will have what kind of numbers, you think? Yeah, 1, 2, 3, 4, or just because Python likes to start from 0, 0, 1, 2, 3. So basically, you get the same output that you get from a classification algorithm, but it's just based on, like how it thinks points are separated. And so another thing that is, kind of obvious, but also subtle at the same time, is that every time you run, there is no preferred order of the clusters. And so this is something that sometimes, like if you run the same algorithm multiple times, you will get, like different results, it looks like, but maybe it's just because clusters 1 and 2 have been swapped, just because there is no order. So it's just something to keep in mind in terms of implementation. Right, so the y-means vector has, as we can expect, a whole bunch of labels ranging from like 0 to 3. And we can actually see what happens here by having the scatter plot. And here, I'm just looking at my training data. And then I'm coloring them by the predictions that k-means is giving me to get a sense of whether or not the points have been classified correctly. And I'm also plotting the centers, which are called centroids. There is another term, they're called centroids because they don't need, they're just a geometric mean, and so the centroid doesn't need to be like a point in the distribution. And there is another term, something like mermoid, but I just think it's because my daughter likes mermaids, and so I'm pretty sure it's not actually called the mermoid, but like there's another word for like algorithm in which the actual centroid is required to be one point of the distribution. So if you happen to know it, let me know. All right, so we did pretty well. It looks like, we had like 4, and then, each one of these clusters has a different color, and so I think we can be happy. Now, I guess we can try and see what happens changing the number of clusters, just to get a sense of, like, do we do worse, better? And one of the things that we could use to look at how well the model is performing, we can't, of course, do our usual comparison of target values and predictions because this is unsupervised. So I don't have the true labels. So one thing that I can do is to look at this inertia variable, which is just the cost function of the k-means algorithm. And it's the sum of the squared distances, actually, the sum of the squared errors, which is, it's an Euclidean distance that you're using that as a tracer. And so this basically tells us that, in an ideal world, well, all the clusters are really well separated. It means that the centroid are very close to each point in its clusters and far away from the others. And so distances between each point in a cluster and the centroid is tiny, and so this becomes small. And in a world in which, like all points are spread out, no matter where you put the centroid, this will be large. So let's see. Here we have what happens for 3 clusters. And it's not that surprising, but basically you get that these and these are well separated enough, and then this one goes in the middle. We could probably fit these for, let's actually take a look at this inertia for 3 clusters. It's like this number of 589. Let's see.
The inertia it's offensive that they used inertia. It should be
I was wondering why.
It should be the moment of inertia because it's the sum of r squared, right? So
it should be what?
The moment of inertia.
Oh, I see.
I mean, to us, physicists, we should be.
Should we email them?
Yeah.
But yeah, we demand more precise. Fair enough. And yeah, I don't know. It's kind of like interesting also because you could call it like a million of things, but. So this is inertia of 599, and for inertia, like low numbers are better and large numbers are not so good. And so with 4, we actually see that there is like a significant reduction on these. And of course, I could say, hey, I think I have 6. And still, this poor algorithm will do its best, and so what happens is that it keeps like 2 clusters relatively similar, and is splitting 2 more clusters in 2. And this is something that we saw last time when we were talking about how can you pick up non-convex shapes for your clusters, because that all the k-means can do is find globes or globules, like or like spherical, like round-ish clusters. And so we thought, having like many of them and then putting them together by hand was perhaps one way of reconstructing a distribution that is not convex. Okay, so what I try to do here is to give you a sense of how you can visualize the evolution of. Yeah.
Okay, so when I do the inertia for 6, I get a better number.
Right, and so this is sort of like the classic trade-off between complexity of the model and lower chi-squared. And so this is what we are seeing also there. And so in some sense, like in the same way that, in like model selections, you're sort of like, trying to find the good compromise between having a model that's not too complex and having like, a decent measure of goodness. Here also, the idea would be that if you plot the inertia, and if you can see that at some point you have like an elbow in how that decreases with the number of clusters, that's probably where you want to be. Which, my take is that it's not that indicative as a way of really finding the true number of clusters, but this is what you're trying to do. And so in general, with more clusters, it will keep going down, right? Because then each point is closer to the center of its cluster. And so here, what am I trying to do? I'm building, so the data are still the same, and I'm starting at a given point, just because this way we can see the evolution. I mean, the reason for that is that I didn't find a way to actually plot the initial guess. You can only like plot where the centroid has gone after the first iteration of the algorithm. So I'm giving an explicit start point for the k-means algorithm, and then I'm saying, okay, I'm fixing everything else here, because if you start from here, you only perform 1 iteration, so this should be doing the same things every time. And I'm basically running this after the initial guess 4 more times. And this should show us, what I'm trying to do here is to show how the position of the centroids change as the algorithm performs more iteration. Normally, if you don't say this n init, if you don't specify these parameters, it will be run 10 times with 10 random initial positions, or far away initial position, or whatever initial positions you define, just because we know that since you're not guaranteed to converge to the global minimum, you want to run the algorithm a bunch of times. And the maximum iteration also, this tells you how many times the algorithm will be run before it declares convergence or just stops. And so here I'm saying, okay, let's run it 1 time, 2 times, 3 times, 4 times with the same initial conditions. And this is probably like not the best visualization, but hopefully will do. So you see here, these like 4 points are my initial guess. And so what happens here is that I'm expecting that all of these points will be assigned to this centroid. All of these points will be assigned to this centroid. And then these points will go with this one, and these points will probably go with this one. And so what you see here is that now this centroid, and notice that like the x scales changes from this plot to this plot, which is the next iteration, right? But basically, all of these points, they were now assigned to a cluster. So when I calculate the mean of that clusters, this basically finds its centroid and has converged. It's not going to move anymore, even after 1 iteration, just because all of these points were correctly classified in iteration 1. Same thing happens here. And here, I'm still debating because I have like a centroid that reflects basically a couple of these points. And so it's like shifted towards the right. And then I have one that probably has as membership like a similar amount of points from here and here. And so at the moment, that centroid is right in the middle. But then the next thing that I do is like, okay, I will assign my points again. So this doesn't change, this doesn't change. But you can see that now, we have more points from this area that are assigned to this cluster. And so like position of this centroid shifts to the left a little bit. And same thing here. And basically by the 4th iteration, you would see that the centroid have converged and the results will not change much as we go along. Make sense? Yes, this is like a question where you can say yes, no, or no. It's not like, okay, I'm putting you on the spot. I'm just trying to continue. Okay. And another thing is like, I want to use the function make moons. So now, we are convinced that if you have data that are well separated and have convex shapes, and you know how many clusters you have, well, k-means works. It's a lot of conditions. So we can take a look at what happens when that's not the case, which is, of course, like the majority of real-life cases. And so instead of make blobs, we can do make moons. Now, what do you expect that k-means will do here? Will you be able to pick up these 2 clusters? No. Why? Can't do. And so how do you think they will divide this distribution?
How many are we going to have it divided into?
Oh, very good question. I would say 2, since we know that the true number is 2. So we're probably going to try with 2. Right. Somewhere in the middle, somewhere horizontally. Basically, like you will pick a blob and another blob. And you can change, like the orientation. I can't predict. It probably will depend in part also on the initial conditions. But it's not going to be able to pick the sort of like smiley patterns. So we can answer our own questions. No, it can't. It can't detect. What's the opposite of convex? Concave? Let's just do non-convex. All right, so let's take a look and see what happens. With 2 clusters, no. I don't know why I commented this. Here we go. And so here you can see that the perf thing has placed the centroids of these 2 clusters here. And so it's like cutting out like this, getting like, a right-hand side blob and a left-hand side blob. Now I haven't played with these, but I'm curious to see what happens, with the solution we were sort of talking about last time, if we make this 10. And so in this case, you can see that by having a large number of clusters, we can get a distribution that is much closer to the real one. But then you will still have to like open this up and say, hey, regroup together these, and these. which is not terribly hard to do if your data have 2 dimensions. But then again, if your data have 2 dimensions, you probably wouldn't be using this kind of methods for clustering them anyway. And so I feel like, yeah, is it nice? Of course, you can keep this in mind as a little trick. Having more clusters help, but I don't think it's a panacea for too many things. Okay, another fun examples of clustering is, how we talked about the digits data set. Now, this is a data set that has 10 classes. It's balanced, and so we can see whether or not an algorithm like k-means will be able to pick up the digits without knowing about them. Right? Without being showing something that looks like an 8 and being told, hey, it's an 8. Can we recognize that there are like this set of different shapes, yes or no? What's your guess? Are you confident?
The distance measure.
Hmm?
What's the distance measure?
The distance measure, yeah, that's a great question. I feel like especially with image data, and actually the more complex the image data, the more important this is, the distance measure is still the distance, like Euclidean distance from the centroid. So you're working with the 64-dimensional feature space, because these are like 8 by 8 images, and so you feature the brightness in each pixel. And so you will find the centroid of that distribution, which is like a point with 64 coordinates, and it will have Euclidean distance in that space. So what do you think? Will you be able to figure out that this? No, yes? Okay, let's see. So we can import our data set. And we can do the clustering. And here, of course, I'm going to tell you, hey, there are 10 of them. Right? This is like the big help that we get. Okay, so right now, excuse me, we have done this like fit predict trick. So we have a predictive membership for each one of them. And one thing that is fun is that even though we know that the centroid is not bound to be a real vector, like a real data point, we can still like look at it and see whether or not the centroid looks like the digits. Because that would be a good indication that if the centroid of each found cluster look like what we expect, then it probably means that the algorithm was quite successful. And so this is not bad, right? So these are the centroids of the clusters that were found. And so this means that, like the most, like if you think about the centroid as like a representative member of each class, it means that, this is done by basically calculating the geometric mean, or, if like in astro language stacking, all the members that were associated to this class. All the members associated with this class like stacked and averaged together, and so on. And so this says that, okay, perhaps I would say 4, 3, 5. This is one of these things that you can only see if you're far away. It's really weird. If I'm here, I have no clue what digits I'm looking at, but it looks better from farther away. So I guess 4, 3, 5, 9, 7, 0, probably 1. I would say the 8 is not the clearest, and then 2 and 6. And actually, I imagine that if you go back to the original data set, which is actually 28 by 28, it's possible that you can do like a little bit better even, just because the fact that we've reduced the dimensionality of the space blurs things a little bit. So this is not bad. We didn't give the labels, but k-means, with the help of like 10 classes, is able to figure out what the representative members of each class are. And there is, in this notebook that I linked from here, which is part of like Jake's book, there are like several examples, including, how you can, what's the accuracy of this classifier, which ends up being, if you use these basically to put labels for your classifiers, then the accuracy that you would end up with is like a little over 80%, which is not amazing, but still impressive, given that you had no labels to begin with. And then you can actually do some pre-processing of the data to get over 90%. And so if you want to look at these, and also there's like an implementation of k-means from scratch, which is it's just like a few lines of code. And so if you want, you're able to look at it here. So far, so good? Yes, okay. All right, so this is what I was mentioning before. the typical method that is quoted as, like helpful to figure out the number of clusters that you can give k-means if you don't know it beforehand is this elbow method. And so the idea is that you can basically run the algorithm for a different, a range of cluster, not cluster size, but you know what I mean, like a range of number of clusters. And then you will save the inertia. And then, at some point you will imagine that the inertia decreases and then plateaus, or at least start decreasing more slowly as you add more clusters. And so somehow you want to be, if there is an elbow in the distribution, you want to be here. However, for example, when you do this in the digit data, I thought, this is a case in which we kind of know the solutions. And so it would be really nice to see that you have an elbow around the 810. So this takes a minute. But what you actually see, at least for me, if I were to see this curve knowing nothing about the digits data set, I don't think I would pick 10 as the most representative number. And so I feel that's why I say overall I'm a bit skeptical. I think that if you're dealing with a science problem, then I think this is, you want to use intuition, you want to look at what's in your clusters, and I think that's in general a better choice than letting the algorithm figure it themselves. I'm sure it depends on the data, but I felt this was an easy enough case where you look at something that you saw above and you're like, oh yeah, the algorithm has really found the most representative members of each class. But you can see that if I didn't have that knowledge beforehand, it would be really hard to be able to pick. You could potentially, yes, I do believe that there is perhaps a change in slope of the tangent right here, but I would hardly call it an elbow.
Yeah, I feel like astronomers have come up with better grouping tools than this k-means algorithm.
Absolutely.
So, okay. All right.
What do you have something specific in mind? Also?
Well, I'm thinking friends of friends, or the density kind of threshold things. They'll be able to find all different shapes, and you have to set some connection level or some linking length or something like that. But I feel that's a little less user knowledge required than something like this.
I agree 100% with you. I think that there is a lot of improvement that can be had, and maybe in the next example will be even more obvious if you're willing to write your custom distance. I think there really a lot of the knowledge and a lot of the effectiveness will come from there. Because now, right now we have all the features and we're giving, equal weight to distances in every direction. And I think there's a lot that can be achieved if you're willing to say, okay, I'm going to sit down, I'm going to think about this, I'm going to think about what features I'm going to give you, and then I'm going to devise a custom metric that says, if two things look similar from this aspect, for me it's more important if they look similar in that aspect. And so I think once you have that, which is still it's a considerable pre-processing, that's when something like this can be successful. But in general, I feel with all machine learning algorithms, that now is it's fancy and it's fashionable and whatnot. But I think this boils down to the same thing. You have some tools. If you don't know how to use them, or if you're not, willing to dig into what your problem is, they're not going to perform too well out of the box. And to go back to your comment, it's actually, so k-means is probably the easiest, the simplest of all the clustering algorithms. This is just an overview of all the ones that are available just in sklearn. And I really can't say that I understand them all, or even a part of them. But there are tons. I wanted to at least look at one hierarchical one, just to give an example. But I feel they're tricky enough. It's tricky enough to understand when to use one that it really takes time. But as you can see, there is a whole bunch, and they give you an idea of what kind of problems they are good for. There's a nice handy table here. However, there are a few that claim, for example, this dbScan or optics, they claim that they can figure out the number of clusters themselves. But I gave it a try in the digits and I didn't find any improvement. In fact, one of them gave me 1,797 clusters, and another one gave me like 2. So, to go back to that, I feel like, if you just like take them face value, I don't think they do very well. But I think that if you're willing to study, okay, what your problem is and to optimize the metric, I think there's a lot that can be done. And you can see that many of them are based on like a graph distance, like a nearest neighbor type of graph. And so I think they would perform more similar to what friends of friends tend to do, I think.
If you run the k-means, like let the clusters go to like 200, it took a while, but then when you make the elbow curve, it somewhere between like 10 and 25.
Right.
So like you can get to that level of.
Oh, that's a very good point. So let's see.
It takes a while.
So I'm gonna, yeah, but you told me already where to stop, so I can make this 50.
And change the plot range.
Oh yeah. Let me do it then in a separate cell. We don't really run everything. Oh no, this is from the plotting, no problem. It's true. I guess that we could probably know that, okay, we don't want to go all the way here, and I have to say, okay, if I look at for the change of shape, it does for the change of slope. So like I don't know, like it's crazy how after college you buried with second derivative. So I can't even remember how these things are called. But I'm pretty sure it's like the tangent of this. And where that changes slope, that means like where the elbow should be. All right, very good. And let me get this out of this, of here, in case you want to rerun. Yeah. All right, so now that we're expert in like all the nooks and crannies of k-means, I thought it's maybe nice to try to do some science with it. And this is actually something that I do it in my class, and I'm using a slightly smaller data set here. But one of the first examples to applications of machine learning to astronomy was classifying the morphology of galaxies. That's because it's a case in which you have like plenty of labels that are given by people, and that you have like several classes, and many of them are easily identifiable by eye. And so my idea here was like, okay, would it be possible to figure out whether or not the classification system that we use is what will come out from the data without supervision? So if I do like a clustering on like a bunch of galaxy images, would I be able to find out that there are like spiral galaxies and elliptical galaxies and irregular galaxies? And the answer is but it's also here I'm working with like a very small data set, and there's like a ton that can be done on images. And so my goal here is just to get to a point to show you that, again, if you're just trying, I don't think the results are good, but it's easy to see what k-means is getting right or wrong. And so I feel like with coaching, then you may be able to get to a good result. And so for this, I'm using these tar files that I posted that have like images, and then images that have been retouched to eliminate some of the multiple sources. And this is something that I did, and I don't recommend that you do here. So I have something that says do not execute this cell, just because when I tried previously, I noticed that a lot of the initial classification were based on how many sources were present in the image. And so I thought I would at least like get rid of something so we could see what happens if you go a little bit further. So are you there? Do you have data? If you want data, do you have data? Yes? Anybody wants to wait while they download the data? Okay, so I'm looking at this like k-means galaxy images notebook. I'm going to assume, and actually the data set is not composed by 499 images, it's only 200. That's because the file was too big. And so I had to rescale it at the last minute. Okay, and this code here visualizes the first 25 objects in the data set, just to get a sense of what images we're looking at. And because I'm generating 25 plots in one time, like I remember the first time I did that, I had to upload my settings in the Jupyter notebook. So if you get an error, like I've placed here a link that should help. And I guess, shall I put this down a little bit since we're working with images? Not that I have no clue how to do it, but I'm pretty sure this is some automatic mechanism.
You want to
SB?
the curtains now?
Yeah, was what I was saying. Yeah, SB. Oh, okay. Thank you. Yeah, I thought maybe just to see some colors. Oh, sorry. Did I interrupt you? I was hoping you could do two at the same time, but I guess not.
Two?
No, this other one, yeah, but. Oh. Wow. Thank you. Okay, so at least we get to see the color a little bit better. So this is just like you have like 200 objects, and they're from a data set that was used by Kaggle, this website that hosts online competitions, and so the data are from Galaxy Zoo. So the original data, I feel like there are like several tens of thousands of galaxies, and these are just like I selected first like a random 500 of them, and then actually I took like the first 200 just to make it more manageable here. But you can see that there are like galaxies of all shapes and colors. And something that happens fairly often is that there are other like spurious sources here, 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 here. And so the first thing that I thought, okay, let me do this just to make our life a little bit simpler is getting rid of those. And I thought maybe, this is this sort of like, make blobs and take out blobs. This is also feel like something fun to use just in case you have to do a little image processing. And so there is this package that scikit-learn has to work with images called skimage. And it has these nice functions called blobdog, bloblog, and blobdog. They have some meanings that I have unfortunately forgotten. They're like, slightly different procedures to find spherical sources. And so here, in this, so this is like a cell that it's okay to execute. And so it just shows for the first 5 objects, it will show us how it found multiple sources. And I also sort of flagged objects for which we have multiple large sources that were detected in the image. I didn't do anything with them. At some point I thought, okay, let me see what happens if I take this out, but I didn't. And so basically what you're saying is like in the first object, 5 sources were found. In the second object, 9 of them were found because it also detects this little one. In this third one, it found 6 sources. In this fourth image, he detected multiple large sources. And I sort of defined a large source as something which is like comparable in size, more than half the size of the central source. And it was this one. And then in this last one, it found like 5 sources. And then this line here, I'm creating a mask, like in all the blobs. And then I'm setting the image luminosity at the mask location to 0, which basically is the same thing of blacking out the sources. And so what you see here in this line is the result. It's not perfect, and I think there's a lot that can be done here at the pre-processing level to make this nicer and to make algorithms work better. But at least you can see that like this big one is gone, this big one is gone, and probably it would be safer to actually cut out a slightly larger radius than what I found here. Okay, so this is the one where I'm saying do not execute, and actually I did it for all 499. For fairness, this should be like 200 in case you ever want to do it yourself. And so I'm doing the same thing that was doing up, but I'm saving the new sources with just like this prefix, just to say, okay, this is the data set I am actually gonna start here. And so this is the first thing that we actually do. We want to read in the images, and then the original images are like 424 by 424, and even with just 200 of them, they're large enough that the first thing I'm doing is resizing them to like 100 by 100. These are RGB images, so they have 3 layers, so the actual size of the image is going to be like 30,000 at the end. And then I'm creating, like, well, this is just like sort of like a big list of the image arrays, and then I'm stacking them together to obtain that NumPy array that I always have to feed to sklearn in order to get something meaningful. So let's do this, and it should take just, I don't know, maybe 15, okay. Like, not too bad. Are we there? And so let's see now the shape of this array is like we have like 200 images. Each one of them is 100 by 100 by 3, where the 3 is for the RGB channels. Okay, so right now, I don't know. I want to use k-means on this data set, but I don't know how many clusters I have. And so I said, okay, let me try with 2. Like the most basic classification that I can expect is, well, if I could divide ellipticals and spirals, I feel like I would already be happy. And that's why I thought, okay, let me see what happens when I try with 2 clusters. And I thought this doesn't look so difficult because usually they are fairly different, at least in color. So even if you weren't to look at the morphology and like to detect things like spiral arms and other substructure, I feel like one of them tend to be reddish, one of them tend to be bluish. And so I was hoping that with 2 clusters, this will work out decently. So let's see here. I have my images, and I can run my k-means. Okay? And so y of k-means will only have 0 and 1s, because it's only like 2 classes. And so, well, this is definitely not the most elegant, but a practical way of figuring out the size of the 2 clusters. So I get 57 galaxies went in one, 143 galaxies went in the other one. All right. So here I wrote a little code to take a look at the first 25, because if this worked, and this is like the let's supervise it part, this works, we would expect the galaxies that have been put in the same clusters to share some sort of similarity. So let's see, I have yk means 0 here, and so I'm only considering this, and I'm reading the images that basically belong or have been placed in the first clusters. This is where having y means equal k0 here, sorry, equals 0 here, and here means. Let's see. This takes a minute just because it's opening and generating the plots. And I have to say, the images that we're looking at as the original one, the actual algorithm is working with blurrier versions. They have been resized, but still. So, what do you think? I wouldn't say that these have a lot in common. This is funny. I wonder why these ones were not found. Maybe because of the color. Maybe they weren't like bright enough in each of the channel. Like this has been like. And you can do the same thing for the same cluster, for the second cluster. So here I'm just changing this to y means equal 1 and y means equal 1. And same thing. What I was hoping would happen is not happening. So the next thing I did is like, okay, let me try with 3 clusters, and let me make my initial conditions slightly smarter. Like, that was, if you don't say anything, we'll start at random. We know that we want to start separated, and we know that sometimes this may be a reason why the algorithm does not converge. So I'm now trying with 3 clusters. And, the spoiler alert is like, this is like the highest number I'll get. And we can now see how big the clusters are. And so we have one with 142, one with 55 and one with 3. So basically the classification has changed very little, right? And basically just like 3 objects that previously were assigned to one of the 2 clusters have been like taken out and like presumably and placed in a different one. So let's look at the small one. And in this case, it's where y of k-means is equal to 2. Right? You can see that, for example, here, I had it as y of k-means equals 0, because in the previous round, the small clusters was the first one. So I'm going to put this 2 and 2. And give him a moment. Okay. So what happened here? Are these similar in some way? I would say yes. These are objects where they have like a very fairly bright background. And actually, in my original example with 500 images, these small clusters had 8. So I guess like I could have shown you, just like you guys don't have the data, but you know, if like I could look at all of them. And so basically this was a cluster that contained most artifacts, or like, you know, weird objects where basically the background luminosity outside of the source was higher than a certain threshold. So this was actually like the first time that I saw something helpful. Is this like a classification in the sense that I was looking for? No, but in terms of like finding weird objects, it was quite effective. So I was, you know, slightly encouraged by this. Then, video people, are you here? Did you find the small weird clusters? We would never know. Okay, so we can now take a look at the other 2. And so the other 2 were let's see, where k-means equal 0. And I'm just going to write it out in the next second. K-means equal 1. All right, so these are the galaxies that have been placed in my first cluster, and as you can see, you know, it's actually, I think, fairly similar to what we saw above. I just think they were swapped. So this is like, you know, according to k-means, one type of galaxy. And let's look at this one. They do, yeah, this is 0, yeah. And this is 1. All right, so we don't have them like one next to each other, but what do you think k-means is doing here? What do you think is it doing? To say these galaxies have something in common and they're different from this galaxy.
Maybe the size of it.
Yeah, I think that, you know, understandably, you know, we thought the color was the most obvious difference, or at least I thought the color was like a striking difference. And, you know, you can have, if not, I would say at least shape, right? How can you think that this shape is the same as this shape? I mean, we also should remember that the actual algorithm is working with a blurrier version, so you lose a little bit of details. But, you know, like, how is this similar to this? It's a different shape, it's different colors, you know, to a human, it's obvious that these are different objects. But this poor algorithm, I think, is placing like the smaller sources in one cluster and the larger sources, in another cluster. Can't blame it also. So I think that probably the most promising step forward would be to somehow renormalize the sizes. Like, since in terms of like morphology, we don't expect, well, I mean, I'm sure there is a correlation. If the size of the image is related to the distance, you know, there is like a correlation between morphology and redshift. But if you don't want to go that route, I think that probably the most promising thing would be like, okay, I see that this per thing is not able to distinguish between small galaxies and large galaxies, so let me just renormalize, or, you know, like do some sort of like cutouts so that typically the center image has always the same size. And I think that this would be promising. Another thing that I think would be promising is to hack the distance measure to say I care about color. And this is in part something that I didn't do for like, on the one side lack of time, but also because I'm still not quite sure of how like RGB images work. And so like right now you have these like 3 layers. And so they're all stacked together. And so in some sense, like, distance in feature space between one point or another, I think has the same weight as like distance in layer space between one color and another. And I think, if you can rewrite your distance metric so that color has a higher weight than brightness, for example, then I think you may be able to get the algorithm to do what you want.
Also the position, right? I mean, if there are 2 things that are two same galaxies, exactly the same galaxies, slightly separated. One is in the center, the other one is towards the left.
Right, but these cutouts, they all have the main source in the center.
Okay.
Right.
So this is like part of pre-processing.
Right, and so I think having the cutout would, you're saying would like also make that problem milder because, yeah, so this is something that I had, like hoped to achieve by like, cutting out the sources. But obviously, as you can see, it's not perfect, and so I'm like working more on that size of, like focusing on like the one source, like making it like a standard size, I think would help.
And how did you choose the size of the cutout? Because if each pixel gets equal weight, then there are a lot of blank pixels.
Right, and that's another great point. Right now we have, you would imagine that if there is like an equal amount of like darkness, it shouldn't matter, but it's true that this is basically also a waste of resources because rather than making the actual image smaller, I could just like cut out the background and this would probably also work. So I'm just going to leave it all as exercises. That's why I have this question. I'm going to show you one more thing that I did in my like, mad rush of like yesterday afternoon. So ideas to fix. So I would say the k-means is classifying galaxies according to size. So ideas to fix, I would say. So what did we say? We said cut out central image and normalize size. We said improve pre-processing of multiple sources. And probably I would say modify the evaluation metric to give higher weight to features like color. I mean, I'm just guessing just because I feel like, visually color is important, and so that's why I'm thinking that color may be one, but there are many ways this can be done.
Yeah, there are some distance measures that are invariant and they're twisting and moving things.
Right, so I think you can explore that, but I always feel like if you write it yourself, it's gonna take
yeah, I think that at least for these digits data sets,
yeah,
there are ones that work much better than the Euclidean distance.
Oh, that's cool. Do you know what? Just are they available or are they?
Yeah, I think there is some. I can look it up.
Yeah, if you look it up and even like want to like post it in the group, that would be amazing.
Sure.
Thank you. Okay, so what I did is like, let me do manual hierarchical clustering. So I figured, okay, if the issue is size, I should fix it better. But then what I thought is like, let me now look at like the galaxy that we place in one cluster. Let me see if I can do splits of that one. Just another way that you can think, okay, maybe to get similarity, you're sort of like now building, well, it's called the dendrogram, but it's like a decision tree where like keep splitting your cluster, and like until you feel like, okay, like the objects in these subdivisions are similar enough to one another. And so for this, I said, okay, now I may have to change the numbers because let's see, Well, this is the second cluster. Which one should we examine? The one with the little galaxies or the one with the big galaxies? What's your favorite?
Big.
Bigger. Okay, so this was yk means equal 1. Okay, so here you can say, okay, now let's build another like 2 cluster classification on the images for which yk means of the original classification is 1. And then I can build a different prediction vector. So now I'm taking the galaxies in this cluster and I'm splitting them. And we can see whether, once we have sort of like corrected for size in this like very primitive way, if we get a subdivision that makes more sense. Okay, so this is done. So this is yk means L, and I'm looking at the first. And so here I was looking at galaxies where yk means was 1, and then on top of that I'm selecting the one where yk means L, the new division is 0. Let's see. And I can do the same thing for the other cluster. I just need to change this. Okay, I got this, and let me just do it also for the one, and then we can see if we think we are improving or not. So I have these galaxies in the first. And these galaxies in the second. And if you only look at this, you're like, oh, okay, well, at least it's picking up elliptical. And then you look at this last line and the last row, and they have to say, I don't think this is, I don't know. I think that, there's a lot that can be done to improve of this. But I think, like, for me, this was a sign that if you're just trying to apply this algorithm blindly, it's not good enough to be able to pick.
Like, this metric is not rotationally invariant, right? So like a galaxy, a spiral galaxy.
That's a very good point. I didn't even think about it.
Like, like it looked like in the first class, a lot of vertical things kind of showed up there.
Here? Yeah. Yes.
Because if you have a spiral vertical and a spiral horizontal, they would have a high. They wouldn't cluster together, right? They would have a high distance from each other if you just summed pixel by pixel the difference.
Yes, because this is just looking at shape, and so if you don't specify rotational invariance, how will we do that? I don't know if this is like purely a pre-processing. It's a very good point, actually. Let me add it to here. I put it here because I think it is so. Any metric should be rotationally invariant, or the data set should be pre-processed to correct for. I'm gonna say orientation. Orientation is not. Well, it's not inclination. Orientation, I guess it works.
Yeah, if you fit an ellipse to every source and then align by the
right. So you could do something like that, so that their like main axis of rotation is something. The one there's spherical don't matter. Or I think again, I can't quite I imagine that there are ways to do it, like within the algorithm. But I think this is probably a bit more annoying, but the simplest way to achieve that. Very good. Other ideas? So these were my conclusion, which is I think the clustering algorithms are powerful when they're like semi-supervised. So you can look for investigations, but you will still have to code them. And then pre-processing and defining a proper distance metric can also help. All right, so let's take a few minutes break, and then we'll look at, as the last things, we'll look at dimensionality reductions and something we can actually do on this same data set. All right, so just like let's have a few minutes for coffee. We can leave this down since we're still working with images, but don't sleep yet. And video people, do you have any questions or comments?
No, but I think that's very interesting comment about the rotational invariant.
Yes, I agree. I'm very glad that there are so many people here who are contributing. I don't know, I can imagine here you could also try to have like many clusters so that at least you achieve like decent amount of similarity between members of the same clusters, and then you can decide which ones you want to group together because they're similar enough for you. So that could be like maybe another thing to try. So I'm gonna add it here.
So I found some paper I can send to you if you want. So basically the idea is that the distance measures should be invariant under all kinds of transformations like rotations or things like that.
Okay.
Yeah.
You sent it just to me, or you guys should feel free to use a Google group for posting, but yeah, I will send it around. Thank you.
Oh, yeah, if I can log on it, 100%. I don't care about that. Yeah, I got it. Okay, cool. Okay. That sounds awesome. Yeah, I got my parents are coming in on the board, and so, if we're definitely gonna be done, that'd be the best. Okay, that sounds awesome. Yeah, so, yeah, if you brought up our, we're good to go. Okay, all right, cool, sounds good. All right, yeah, thanks, Tim. No, a week is totally fine. It's like, it was gonna be like 3 weeks or something. Yeah. All right, good, thanks.
All right, and we're on. So the last thing that I promised to talk about a little bit, and actually it's another like huge, super interesting topic in which we are going to barely scratch the surface, is dimensionality reduction. And the idea here is usually it's used for a couple of things. One is because sometimes just like the sheer size of your data set is large enough that you need to find a way to make it more manageable. And in many other ways, it's used to build some sort of like understanding of your data. So when you have like a ton of different features, and you want to like sort of project it down to the space that can best summarize information within a few variables, then maybe also understanding what those variables are is helpful just to understand your data better. And there are many of them. We're gonna look at one which is like a very simple one. It's like PCA, Principal Component Analysis. It's simple, but I feel like, again, understanding simple things, I think it's a good stepping stone to go to the more complicated ones. And I feel like this is, I would say, good enough in many cases when what you're trying to do is working with something which is more manageable. So we're going to work with two sets of data. One is SDSS spectra, and so this is like this file, like spec 4000 corrected or something like that. It's an adaptation of an example that actually is on like the sklearn website. And the other is we're going to try and see what happens to dimensionality reduction on the same images that we've been working with, just because it's fun to see it in two different contexts. So here, nothing new. We are still using these packages, and then like the new, all of the, actually not all. There are two models in sklearn that tend to be relevant for this. One is decomposition, that has things like PCA and friends. The other one is so-called manifold learning, which is more geared towards having a low dimensional representation of your data that conserves some sort of like structure of the higher dimensional data. So PCAs, the classic PCAs, have tough complexity. It scales as order of n3, where n is a number of features. So not the most user-friendly, but the ones that actually is right now implemented in scikit-learn already has some randomization built in, so it's not bad. Okay, so let's load some data, and these are like a bunch of spectra of galaxies from the SDSS survey. I think there are 4,000 of them. And it's a special format, so we can access the data using this language. And so basically X is an array that contains the spectra. So basically like wavelength by wavelength, the intensity or fluxes. And these labels, these were labels that have been given to this data set where, like it already underwent some classification process. And so they gave them label, hey, I think this is a quasar, I think this is an emission line galaxy, I think this is a quiescent galaxy, so I think this may be a star. And so this is what's in these labels. So the shape of our data is like we have 4,000 examples, and each one of them has 1,000 attributes. You can think about it as like the measurement of like the spectrum intensity at 1,000 different wavelengths. And Y is basically the classification of each one of these objects into a specific class. It's not particularly illuminating, and so we can look at labels. And so this tells us basically what these numbers mean, right? And so a galaxy can be classified, actually an object can be classified as unknown, or a star, an absorption galaxy, or just a galaxy, or an emission galaxy, so narrow line quasar, broad line quasar, sky, high rush quasar, late type star, and that's it. And so basically these, you can imagine that hopefully absorption galaxy and emission galaxy, these are like the most recurring, and so like a ton of these labels will be 3, 4, and 5. Actually, I should say 2, 3, and 4. Okay, so this is a code that just plots a bunch of examples, and so we're just looking at the first 10 galaxies on our data set, and I'm just like shifting them a little bit so we can see them. So you see like the spectrum for the first 10 objects, and then the color, so that there are like 10 different colors, which is a bit misleading. Maybe I should have colored by label. But you can see that they have different shapes, and so for example, the first, it's an emission galaxy. You can see that it has like several strong emission line features, and so is the last one. Now this is, it's interesting, but it doesn't tell us anything about, the characteristic of the data set overall. And so what we're doing here in this next example is like we're plotting basically the first occurrence of a galaxy for each class, for the most common / interesting classes, right? So like, getting out something like, unknown stars that are not of particular interest to us if we're studying galaxies. And so this basically tells you, okay, these are different examples of objects that fall into this category. The offset is artificial. This is just so we can see the data, but you can see that, in general, different shapes will correspond to different types of objects as we expect. Okay, now what does it mean to do a principal component analysis of these data sets? I don't know if I actually have the formula, but the simplest example of PCA is linear PCAs, which means that we look for the 5, 10, 20, like for a basis of 5, 10, 20 spectra-like objects, so basically arrays of 1,000 attributes, so that the majority of the variance, actually I should say, so that every object in the dataset can be described as a linear combinations of this component. And we choose the one that gives us the highest accuracy in this remapped representation. So what does it mean? That if I have a dataset that has 4,000 objects, and I decide to describe it with 10 principal components, it means that rather than having to save, for example, 4,000 arrays of 1,000 numbers each, I now have to save 10 arrays of 1,000 numbers each that are the principal components, sometimes also called the eigenvectors. And for each galaxy, I only have to save 10 numbers, which are the coefficient of this linear decomposition. And so this is where the dimensionality reduction comes in. I go from a data space that had 4,000 elements of 1,000 length each to only 10 of them, plus the 10 coefficients that I use for every galaxy. And so the principal components will be, in some sense, what they correspond to is, if I look at all the variation or variance in my data set for these 4,000 galaxies, I will pick the 10 components that can explain the maximum variance. And so in the end, this means that when I project down my original spectra to these 10 components, and then I compare the original to this lower dimensional representation, I expect to find a small difference if the representation is good. And of course, this is something that, again, I can imagine that I can do better with 20 components than with 10 or 5, but where I put my cutoff depends on how, what matters to me, how accurate I want to be, and how much of this dimensional reduction I want to achieve. So we can do this here. And on top of that, looking at what these components are sometimes tells me what are the most important features that make different objects different or similar. So in this case, let's see. As usual, it's 3 lines of code. What I'm doing here is normalizing the datasets. In many cases, this helps just because you're looking at galaxies and luminosity may differ a lot between galaxies if they are a very different redshift, but typically what you care for is the shape. You want to say the objects are different if they have different shapes, and so it's usually helpful to normalize all of them. And then we can just do like a decomposition. And here I'm using 50 components. I'm fixing the random state just so you know it should be reproducible for all of us. And then my projections is called PCA fit transform. What did I do? I didn't execute this initial cell. Here we go. Okay. Oh. Okay, so this is done. So I want to look at the shape of this. So basically what this array now contains is for each one of the objects in my dataset, 4,000 of them, I have, instead of 1,000 number, I have 50. This 50 are basically the coefficient of the linear decomposition of each object into its principal components. Okay, so this plot the eigenspectra, right? These principal components, let's see, are they going to have some meaning? Probably I don't want to plot all 50 of them, so I'm just going to go with the mean that doesn't have a lot of information because it's just like the mean of everything, and then like another 4 of them. So now this, like the mean just tells me, okay, if I average everything in my data set, how does it look like? So it doesn't carry too much information. However, these, the first components, like component 1 is like, okay, this is, if I were to describe anything as like, a variation of the mean plus another component or another template, this is the one that has the highest amount of information. And so what this is telling me is that I care for color and for strong emission features. And this is mostly the component 2. Right? So we can reinterpret this saying, okay, if I have to pick what is that makes spectra most different from one another, so that if I had to pick only something, what would I pick is I want to look at the overall slope of the spectra, which makes sense because red galaxies and blue galaxies are most different from one another, and I want to pick strong emission components. And this is probably just here to compensate for the bump here, so they can achieve any combination by combining these two. And so this is how you do PCA. It's quite important. It's quite simple, and we can interpret this eigenvector as the basis that explains most of the variability in the data. Now we've done that, but we haven't shown that this works, right? Okay, we projected down to like 50 components, but how can we check whether or not these projections are somewhat similar to the original? Because if they are not, if the representation that I obtain is not a faithful representation, then of course this is not particularly helpful. And actually you will see here that this is not working particularly well, although the reason for that is that there are strong emission features. If you're willing to process them separately, you actually can get really brilliant results. But anyway, the process of doing the inverse transform is also very easy. So this is basically taking these projected components and projecting them back in the original space. But you're only working with 50 numbers, so there's not going to be perfect. So this is building. I wanted to actually do it from scratch rather than using these, because for a linear PCA this is simple enough. You're really looking at the dot product between like your component vectors, your projection, like your coefficients vectors, and the matrix that we built with the components. But I have to tell you that I couldn't figure out how to make the inner product work. And I was running late, so I'm like, okay, let's just use inverse transform. But it should be like, easy enough to do. And so now these are like the reconstructed objects, and these are the original objects, and we can plot just like 4 of them. And so you can see that actually, overall, this is probably working, but it's far from perfect. And in particular, there are some things, like these objects in particular, where the behavior here in the, what is this, let's say UV optical, like in the bluish, is actually not particularly well captured by them. Now, I know for a fact that, the struggle here comes from the high amount of short scale variability. And so I've done this exercise for my research years ago because I wanted to look at stellar libraries And I was like really frustrated by having to, reread the spectral libraries of when I had to do like SED fitting. And so what I did is I did like a quick PCA on the spectrum without emission lines, which is actually works quite well even with 4 or 5. And then I found an analytical fitting function to the coefficient as a function of the parameters. And I could generate like any spectrum that I wanted from command line. But it's not terrible. And we can look at another few of them. This I always like, let's say if I do 4, 8, I have to do this -3. So this is another 4. And so I feel like, you can also see that for some of them, it actually works quite well. And usually like the high variability ones are the ones that are a bit trickier to work with. Okay, so this is the reconstruction. And here also, we can use some sort of like elbow method to figure out, okay, what is a number of components that could be a good compromise between being able to explain enough of the variability in the data, which means having an accurate reconstruction, and keeping the dimensionality of my new data set small. And so this, PCA methods also have this explain variance ratio. So we can plot that. And you see here that while there is a slight improvement as you go beyond 10, for this particular data set, 10 is probably a good number. So in this case, usually the elbow tends to work quite well. So this means, okay, if I go back, I will probably like pick 10 instead of 50, because this means that, for every galaxy, I can now just save 10 numbers. So far, so good? All right, so the last things that we will do is see how this works on the galaxy images we were working with. Like I do a spectra, should also work on images, and images are actually, just because of being like two-dimensional, sometimes having layers, they're even more expensive as data. And so on images, it's particularly important to being able to do good dimensionality reduction. So here I'm working with exactly the same data set, and this read-in is exactly the same that you had on the previous one. And what I'm doing here is that I did my dimensionality reduction on each of the RGB channels separately. And I don't know if this is optimal. This was like the only way that numerically I was able to figure it out, just because I felt like this is just because of my limited skills working with RGB images. I think there are probably ways in which like you don't need to do it channel by channel, but this is the only one that I found so far. And so now basically I created, I extracted each one of the channels. So this is like R for red, and this is basically a reshaping of my image array that has like 200 objects and a whole bunch of features and 3 layers, and I'm taking the first layer. Right, so just extracting the red. And I'm now left with a data set that has 200 objects. Each image is 100 by 100, so I have 10,000 features. And I want to bring this number down to something more manageable. So rather than having to save, like 1,000 numbers to represent each object, I want to have something smaller. And we can try with 100. This is like, a factor of 100 reduction, so it's sizable. I'm doing the same thing. Okay, let's see. So the new shape will be like 200 objects, 100 features per object. And let's see, the components are what in the estimator are my eigenspectra, which actually in this case they're called, like in the jargon of they're called eigenfaces. But of course, like eigenfaces doesn't quite apply to this, so we can think of them as eigengalaxies. And so if we had, to come up with the Platonic idea of a galaxy, probably looking at the principal components of a large data set, hopefully would show us what we have. And we can plot the first 50 of them. Now, I don't really expect, do we really expect that we need 50? I can tell you that, in most image processing problems, 10, 20 components are more than enough, and then typically what you start seeing is noise, but I'm plotting 50 just because we can. And so here we are. So I mean, I guess like somewhat unsurprisingly, like the first is, which I don't think this is the mean. So the first is like a blob. The second one is another blob. And then I guess we have like a bunch of components that basically allow you to describe galaxies that are not spherical in shape and have different inclinations. Again, something that I imagine that if you were to reprocess the data set to sort of like correct for orientation so that like all galaxies have the same orientation, I imagine that this could be improved and you can like squeeze this down to a much smaller number, just because like elongation will be something that you only have to account for in one direction. What you can see here, basically you're looking at the same thing but just sort of like slightly rotated. And then I feel like most of these I would say have to do with having like multiple sources, because they seem to be like combinations or like different brightness blob in different places. And then from here on, I think we'll have a hard time saying we're looking at anything different from noise. From like, let's say, like the third row onwards. So we can also see here if there is like an obvious optimal number of components. So if you have to pick, let's say, what would you bet on? Where do we expect to find an elbow? And this sort of like explain variance score. This is 5 by 10. 13, that's nice. Any other takers? 10. All right, I think, yeah, we have like, yeah, 2 guesses. Probably not gonna be better than this, so let's see. All right, so I think like this is, I mean, again, it's debatable. It's certainly, I would say, probably somewhere between 10 and 20. Like maybe like a bit closer to 20, which may or may not make sense. But yeah, definitely, once you get here, I mean, you're still improving, but just like not quite as much. Okay, so last thing, and yeah, I really believe it's the last thing, is we want to now reconstruct the original images. Like we brought them down to 100 numbers instead of 10,000. So that would be nice. Usually if you can like, bring your data set down by a factor of 100 is nice. And same thing, we just do this like inverse transform. And then we can plot. And so I'm gonna plot here for, I guess, like 5 galaxies, the original on the top and the reconstructed projection on the bottom. So you see, it's not bad. You'll definitely see that you're losing some small scale detail as you go from this row to this row, right? So it's like, okay, you have a slightly blurrier version. So according to what kind of science you're doing, this may be enough for you, or it may not be enough. And so you may want to play with that number to see what you can do. And in general, this is something that is used a lot, for example, as a pre-step to clustering. And so, like this is another way, you can decide whether or not you think like enough information has been conserved from one to the next. But, especially because clustering algorithms often have fairly poor scaling with number of features, just because they have, like the distance are calculating in every single feature direction, that having these as pre-processing for clustering or other science is actually quite common. One of probably like the most common application of these. So this is for like just one channel. So you see a grayscale. I also attempted to do it for all the 3 RGB channels at once and put them together. I couldn't, as you can see here, I couldn't be bothered to do like a for loop of some sort. So I just like copied and pasted 3 times. And so now I'm reconstructing the R, G, and B images and plot them. As you can see, something funny happens. So I'm pretty sure that, as I was saying, these things come from my limited abilities in working with RGB scales, and so my guess is that these are pixels in which, like 2 of the channels are completely muted and the other one isn't. And I think, like, I'm sure that there is like some smart way and also some like not so smart way to deal with it. I just didn't have the time. But actually, if you look now at the images, I would say the color and the shapes are fairly well represented from like the first row to the second row. And so I would take these as a successful example of dimensionality reduction for these images. It's kind of like it's nicer when you can actually see it in color if there is really like not a lot, at least visually, not a lot of information lost from one to the next, from the first row to the second. No? What do you think? Nice? Good? Yeah? Works? Let's see. Another 5? This is like, oh, this is not even the original. Let's see, was I cheating? No, I guess, I mean, if you don't mind the confetti here, I think it's like a pretty decent example of reconstruction with 100 components. Any questions, comments?
Just one note that the original tar file with the images, it didn't quite have the right images in there. It didn't start at 0.
Oh.
And so some of the code has to be.
Oh no, sorry about that. Okay. Is it like, did I just put like the
It goes
0?
from 1 to like 199 and then 203 to 206. It's like some kind of funny.
Oh, sorry. Yeah, because like I tried to upload the 500, I couldn't, and then I had to just like manually select, and I guess there's something failing here. Okay. So what's the easiest way? Is probably to.
So where it loads them, if you just change I to I+1, then it'll start at 1, and it gets most of them, and then you just have to change some numbers.
Okay, or I could just maybe re-upload the correct data set.
But so how are you getting the there's some places where like this where you're showing the 10 by 10 and it has you reshape. How are you?
Yeah, so I just changed. If you go up, the first time it reshapes, instead of doing range 200, changes to range 199.
Is
From
this
1 to
happening?
199 are in there.
Is it only with the image or also with the no sources image?
The no sources looks like.
Okay, so the image was like a one in which I. So maybe though, I think maybe I can just like re-upload these with the proper files, and this will fix it. Sorry about that.
Okay.
Or I guess another possibility is that if you want, you can also just load the no sources images here, and that should also work. I mean, it's not like as important for dimensionality reduction, but you can work with that data set that doesn't have this issue. So this is pretty much it on my side. I wanted to, since we have like a few more minutes, I mentioned that it's common to use some sort of dimensionality reduction as pre-processing step for clustering analysis, but you can also sort of like use clustering itself to do dimensionality reduction. And so maybe we can look at this example here. And this is like the book I was telling you about, and you can recognize some of the stuff that we did. But this is something that I also found quite interesting. And so, for example, you could do clustering to achieve like color compression with images. So this is an example of, well, a picture with many colors. And in general, any like JPEG picture, it's a 3D array with red, blue, and green colors as integers from 0 to 255. And these are these are like the pixels in color space, and overall there are like 16 million possible colors combination. This is like the red versus green distribution for 10,000 pixels in the image, and this is the red versus blue distribution. And so the trick here was like, okay, we could do like a k-means clustering across the pixel space to go from 16 million colors to just 16. So this is, like it's sort of like I found like an interesting way of doing something that you usually do with dimensionality reduction with clustering. And so I feel like there's a lot of overlap between methods that are presenting as one on the other. So take these like 16 million possible color, cluster them in 16 clusters, take the center of each one of these clusters as one of 16 possible colors. And so this is the reduced space, which is, it's less brilliant. Overall, you can imagine that losing some of the extreme examples and sort of like, averaging everything out gives you slightly less brilliant hues. And then you have the 16 color image on the right. It's, not quite as nice as the first, but there is like, like about the factor of 1 million dimensionality reduction from left to right. And it's still like, all the structure that was in the image is still present from left to right. And so I feel like for me, this was like a really like nice thing to look at as, like an example of using clustering in a more creative way than what this is usually used for. And one last thing is that, there are tons of dimensionality reduction technique. I only talk about PCA and the linear case, which is the simplest. But there are kernel PCAs, which like make use of the kernel trick to project down in dimensions that may not be available to a simple linear decomposition, and so they're quite powerful. And more complicated things like T, S, and E. These I feel like they're popular. We have used it actually in our paper. I think what this is very good for is taking sort of like keeping a similarity measure between like a large dimensional data set and a small dimensional data set. So that basically they give you a measure of similarity so that they project data in 2 dimensions so that if 2 points are sort of like similar to one another in the high dimensional space, they would also be close by in your new plot. SOM, these are like self-organized maps. And I think that I just put this link here. And this is something that we saw briefly in the beginning, and this gives an idea of how, like, how many different methods you have to sort of take this like 3-dimensional data space and project it down. But I think like it takes quite a while to understand like the technicality, and so that's why I decided to just like stop with the simplest one, which is the linear PCA. But all in all, I think we're all set. Do you guys have any other questions or comments? No? Well, thanks for coming. It was really a pleasure to have you. And as you know, I think probably by now I really like to have all the service, but I will send you a form if you want to send some anonymous feedback, just in case like we do this again, or maybe like another way. It would be great to hear what kind of things you enjoyed the most, what kind of things you think could be done differently. There were like topics you didn't think were necessary, or other things you would have liked to see. And other than that, I think we are done. Yeah!